Juven, are you going to give an introduction?
Me? No, not today. You will give it.
You're sharing your screen. That's why I asked.
Yeah, I share screen just for the sake of making them see something funny.
Okay. Oh, and there's my. Hey.
Oh, hi. Sorry, does my video look okay? Because my video is messed up on my computer, so I can't see my own image.
Yep, I see your head,
Okay.
and
Okay.
I guess you have a green screen behind you, but it's
I do
just
have a green screen, but I'm not going to use it, so it'll just be green behind me. Actually, maybe I should try sharing my screen. If you'll, but I think you need to let me do that. Because something happened with the Zoom update that happened on March 23rd. And so then after that, my video looks really weird. It's like I can't see my own face. Let's see.
Maybe you have to try changing your view. I don't know.
Changing my view.
Like you see where it says view in the top right, maybe there's an option there.
Plugin is required. Oh, I have to. Oh, I hope this works. I didn't actually try since this update. I haven't tried sharing my iPhone or iPad. I hope that'll work. Let's see if this works. Okay, so let's see.
Welcome, Michael.
Hi. How are you guys doing? Okay, so you see that looks promising. All right, so that's okay. You can see my screen, right?
Yep.
Awesome. Say I can change my, well, I'll try doing that after this, I guess. So you guys are you're not on spring break, I take it.
No. Actually, I'm not sure when it is.
Oh, well, I guess for you guys, there's less meaning to spring break if you're not teaching.
Yeah.
I don't think we have one, actually.
Oh, really?
Yeah, they broke it up and distributed it amongst like various random single days off.
Huh. I was trying to remember. I feel like when I was in college, we had spring break, but I don't have very many memories of it. Somehow it didn't make much of an impression. But yeah.
I mean, we usually do. I guess they figure no one's going to be traveling this spring break.
Oh, this specific spring break you're saying.
Yeah.
I got rid of.
So it's just random days in the semester.
I see. Yeah, we're technically on spring break now, but it doesn't feel much like spring break. I mean, my kids are home from school. That's the only difference, really.
So we'll wait maybe one more minute for people to arrive, and then we'll start, okay?
Oh, sure.
Okay, so let's get started. Welcome everyone to the CMSA Quantum Matter Seminar. Today we're very happy to have Professor Michael Levin from Chicago to tell us about an introduction to Stringnet Models. Actually something that he's quite famous for, so we're very excited. Thank you, take it away.
All right, thanks for giving me an opportunity to talk here. So yeah, I'm going to be talking about Stringnet models. I'm mostly going to be, most of the talk will kind of follow this relatively recent paper that I wrote with Chen-Hung Lin and Fiona Burnell. But just to be clear, this subject is, I'll say a little bit more about this. It's an older topic, and a lot of things I'm going to be talking about aren't really that new. So maybe let me just start off with a few comments about Stringnet models. So first of all, what are they? So these are exactly solvable lattice models. As we'll see, the Hamiltonians that we're going to write down are sums of commuting projectors. So you can sort of solve them pretty much completely, find the ground state, excited states, and so on. And they're exactly solvable lattice models that can realize a large class of topological phases. And here, when I say topological phase, I really mean it in the sense of anyons. So these are, I say topological phase in this talk, I just mean a gapped phases with anyons. So symmetry, in particular, symmetry will not be playing an important role in this talk at all. I'm not going to be interested in realizing symmetry protected topological phases or symmetry enriched topological phases. It's really just going to be all about realizing phases with anyons. But at the end, we'll talk a little, I'll mention some open questions about incorporating symmetry into the discussion. Okay, so these are solvable models that can realize topological phases. So a few more comments. So at some level, you could say these are generalizations of the Torah Code model. Probably most of you are familiar with this model. It's an exactly solvable model that realizes basically a Z2 gauge theory. And these Stringnet models are some kind of generalization of that particular model. Another comment is, as I said, this is kind of an older topic, so it's probably maybe the original paper on Stringnet models was written in 2004 with Xiaogan Wen. So why am I talking about it now? Well, partly because people are still interested, still want to understand it, but it's also partly because it's sort of a little bit technical, but the original paper made some additional assumptions about sort of some additional restrictions on how the Stringnet models were built. And so it wasn't kind of as general as it could have been. And I think that's been known for probably at least 10 years now. But what we wrote in our recent paper was just a kind of very thorough discussion of how to correctly generalize the models. Previous papers had already generalized them, but maybe hadn't put in all the details. So part of the point of this talk is also to kind of explain the more general description. And as I said, in this talk, I'm going to discuss this general case, and these sort of more general Stringnet models we call generalized Stringnet models, for lack of a better term. Now, I should say I'm not going to do the absolute most general case because it just makes the notation really hard. So I'm going to make one simplification. Maybe if you don't know what this means, don't worry about it. But for the experts, I'm only going to consider the case without fusion multiplicity. You can ask me about this when it appears, but it's easy to generalize what I say to cases with fusion multiplicity, but it just makes notation more complicated. So, I'm going to make that one simplification. Okay, so all right, so then I guess I can just start then. So I'm just going to start off by telling you how to build these Stringnet models. So how do they work? So first I have to tell you what Stringnets are. So this is sort of supposed to be a typical picture of a Stringnet. It's a kind of graph drawn in the plane. The edges have labels that different. Here the labels are 1 and 2, but in general, it's some kind of graph with labels. Now let me say a little more precisely what it is. So it's a planar graph with a few properties. So the first property is that the edges are labeled by some finite set, which I'll typically call A, B, C. And this set of edge labels are we'll often call string types. And we'll call the edges strings. So we can sort of think of a string net as a network of strings. Sorry, there's a delay here. A network of strings, and they come in different types. Okay, so that's what these ABCs or these 1s and 2s are. Okay, so fine. Another property of the edges is that they are, I'm going to assume, and I'll explain this in a little more detail below, but just for now, I'm going to assume that they're sort of piecewise differentiable curves. So they, as you can see here, I drew them as like piecewise linear of lines, but in general, they could be curves, and I'll even allow, you know, something that's like corners and things like that. But I'm going to make an assumption that there's something called no vertical bending. I'll say what this is in a moment, but it's a particular assumption about how what these curves look like. So I'll explain this later. Okay. The third property is that the vertices of this graph, they're either bivalent or trivalent. So all vertices have either 2 edges or 3 edges. The bivalent vertices always look like one of 2 types. So they always look like this, like either a V or an upside down. And furthermore, they always come in this particular structure, A, and I'll explain what A bar is in a second. It's either, it always comes in a pair, A and A bar. Now, what is A bar? So A bar, for every string type, we assume there's some corresponding string type called A bar, which we call the dual string type. So this is a piece of data you have to specify when you write down a Stringnet model. In addition to specifying the set of string types, you have to specify the dual string type for every string type. You have to, or mathematically, you have to specify this involution on a set of string types. And once you specify that, that tells you what are the allowed types of bivalent vertices. And they look like this. Okay, roughly speaking, A bar is kind of, you can think of these string types as sort of like particles, and A and A bar are kind of like particle and antiparticle. But anyway,
excuse me,
so that's the,
sorry,
go ahead.
Sorry, Michael. Did you write edges are piecewise differentiable? Or
yes.
But why do we require a differentiable there?
It's not super important. You'll see below, just to define this notion of vertical bending. Maybe it's the technical assumption. Basically, I want to make sure that well, let's come back to that below. It's just to precisely define this no vertical bending rule. It's probably not important. There may be a way to get around it. Okay, so the bivalent vertices look in these 2 types, like these V or upside down V, and it comes with A and A bar. And similarly, the trivalent vertices also come in 2 types. They always look like this or this, these like a Y or an upside down Y. And again, the allowed string types that can meet at the vertex, there's some restrictions on them. Okay, so in particular, there's some kind of list of branchings that are allowed, like ABC type branchings that are allowed. And only those types of, and that's another piece of data that you would specify. It's something called the branching rules. So once you specify the branching rules, specifying the branching rules is specifying these triplets, A, B, C. And to be clear, yeah, I don't know how much detail you want, but it's an ordered thing. So you specify a triplet ABC correspond. If an ABC is in your list, then precisely these 2 types of trivalent vertices are allowed. So there's an ordering here, which is important. And I also put a semicolon here to emphasize that C is kind of the there's kind of a, well, you'll see in a second, but there's kind of a lack of symmetry between C and A and B. And the reason why there's a lack of symmetry, as I'll explain in a second, is there's like a time direction that's going to be important. So this vertical direction plays a particularly important role. And so there's this kind of difference between C and A and B. So that's why I put a semicolon here. But in any case, you would specify these triplets, and that would tell you that the allowed trivalent vertices. I think there was a question.
Yes, Michael, you can answer this later, but for the case of the Torah Code, what would this, if you could just orient us with the Torah Code, what would the trivalent vertex be for the Torah Code?
So for the Torah Code, the string types, there would only be 1 non-trivial string type in the language I'm using now. it's either one or two, depending on your, I'm not including the so-called null string so far. So there would only be one string type in the Torah code. And the branching rules would just be like saying that, you know, what comes in must come out. Like if you have, if basically you would allow, C could be the non-trivial, you could have, and actually there'd be no branching. I think that would be the rule. So there's no branching at all in the Torah code. That would be the rule. So there would be no allowed trivalent vertices, in fact, in the description I'm using. And so that would mean that your graphs would just look like closed loops without any branching. Does that answer your question?
Yes, thank you.
Yeah. Yeah, I'm going to give an example in a second. So actually, that's the next thing I'm going to do. So just to summarize, the basic data you need to describe your stringnet. Your stringnets are a list of string types, a set of dual string types, and then these branching rules. Sometimes people, yeah, branching rules. So let me give you just an example. So let's go back to, here's an example of some data. So you might have a model that has two string types, say 1 and 2. And the dual string types are 1 bar is just 1 and 2 bars just 2. So it's kind of the most kind of boring case. And you might have these branching rules. So these say these are the particular types of triplets that are allowed. Okay. And I think I'm missing one triplet, actually. I meant to put 2, 2, 2. It's another triplet. Okay, so these are the allowed branching rules. And so then here's that diagram I drew before. This would be an example of a allowed sort of stringnet for that data, right? Because if you look at each of these vertices, you can see, you know, here's a 2, 2, 2 branching. That's an allowed thing. Here's a 2 branching into a 2 and a 1. That's probably this one here. So each one of these vertices you can matches one of these 4 types. And you can also see that
That's another question here.
Mm-hmm.
So on the rightmost graph, there seems to be a bivalent vertex, which is not of the type you wrote down. It's vertical.
Very good question. Yes. Thank you for asking. So yeah, so let me mark where the vertices are, because it's a little confusing with these diagrams because I allow them to be piecewise differentiable. So sometimes you might have something that's not really vertex. So let me mark where the vertices are. So this is a vertex. That's let me first mark the bivalent vertices. This is a bivalent vertex. 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 Okay, so I'm only marking the bivalent ones. I guess the trivalent ones are self-explanatory, but in answer to your question, this is not a vertex. Okay, this is a single, and that's why I only had one label here. I just had a 1 here. This is a single edge that just has a kink in it. I only drew it with a kink. It's not, you could have drawn it as a nice smooth curve if you wanted to, but I drew it with a kink because I don't know, that's the style of way I draw these diagrams. So this is not a bivalent vertex. Does that answer your question? This is just an edge that it's allowed to have a kink or a curve, whatever you like.
Yes, thanks.
Yeah, thank you. That's very important. So
what happens if
you
you rotate one of the pictures? So imagine you rotate it. Will this change where you put the, I'm trying to understand the difference between.
Very important. We can't rotate it. So this is that's what I'm going to get to next. There's no vertical bending rule. The vertical direction plays an important role. So if you take one of these diagrams and rotate it, you may get something that's illegal. Okay. It's important that there's a vertical direction. So this direction here, as I'll say in a second, you should think of as like the time direction. So I'm going to say this in a second. Maybe we'll come back. Maybe I can just say this one thing and then you can ask the question again.
Well, you did answer my question. You're
okay,
not allowed.
Great.
Okay.
So let me explain this no vertical bending rule. So what is it all about? So roughly speaking,
Michael, sorry.
Yeah.
Just make sure the comment there were you trying to say that you need to put these graphs on orientable manifolds? Are those the statement related?
Well, actually, I'm usually going to be thinking about putting it. Yeah, I don't know if it's orientable, which is so important. You need to have like a particular direction, which is picked out in space. Right. So actually, I'm always going to be thinking about these as just on a disk. So I'm not worried, although your question is if you extend it globally to a whole manifold, how would you do that? Indeed, I'm mostly going to be thinking about it on a disk. You could probably do it on a torus too, but I want to be able to pick out a vertical direction, like a particular direction, which is like the time direction. There may be ways to get around that if you want to put it on more complicated manifolds. But for the purposes of this discussion, I'm only going to be thinking of them in a disk. and have a particular assigned like vertical direction. Okay, so what is
May I
this
ask
no
a
vertical
question?
bend? Yeah.
Yeah, sorry. So I was just wanting to make sure that these Stringnet models so far, while you haven't introduced any quantum mechanics aspect of it, but I should think of them as world lines instead of what's happening in the Hilbert space. Is that correct?
Okay,
Because
that's a good question. No, these are states in the Hilbert space, but as I'm going to explain, their mathematical structure is inspired by world lines. So these are going to be states in a Hilbert space, but indeed, that's what I'm about to say. You should think of them like to understand the logic, like why in the world would we ever think about diagrams of this form? They're inspired by world lines. Okay, so let me say that right now. So you should, to understand this no vertical bending rule, it's kind of nice to think of this direction as space and this direction as time. And then you can think of these stringnet diagrams as describing world lines of particles moving. And then the no vertical bending rule basically says the particles have to move in a reasonable way. They can't go back in time. Okay, so let me give you an example. Like, so this is allowed. Okay, so this is just a particle that's moving to the right, moving to the left. No problem, right? So that obeys my no vertical bending rule. This is also allowed. Again, particle moving to the right, it stops abruptly and then moves to the left, right? This is not allowed. Okay, this would describe something where a particle goes forward in time and then back in time and then forward in time. That is not allowed. This is also not allowed. Again, this is like the difference between these two is I try to draw these as sharp corners. Again, it's like a particle going forward and backward in time. On the other hand, this is allowed. What does this describe? This describes, so notice these are supposed to be vertices. Maybe I should emphasize that. But anytime you see two different strings meeting like in a sharp corner like this, it's a vertex. So I often won't draw those points. But why is that allowed? Because this describes, well, physically this describes like a particle and a particle antiparticle pair being created and then then fusing with another particle. So the key point is that we don't allow any curves like this. The only way we ever allow anything like this is if there's actually a bivalent vertex involving a particle and an antiparticle. Okay, and so this is really the only way you can get something that looks like vertical bending. And when it happens, it's not really a single edge. That's the key point. It's actually made up of three edges, an A bar, and another A. Okay, so that's the no vertical bending rule. It basically means that if you want to say it formally, the tangent to your curve always has a non-zero time component, and it can't abruptly switch from a positive time component to a negative time component without going through a vertex like this.
I see.
Okay, so
Thanks.
So these are the allowed types of diagrams. I should also say I won't draw orientations on these lines, but you should think of them as being oriented kind of in the time direction. There's a natural orientation, which is kind of like this, always pointing upward. But because we have this no vertical bending rule, we don't have to draw the orientation because it's defined once you draw the diagram, right? So I'm not going to draw orientations, but in case it helps you, you can think of those orientations as being there. Okay, so those are the rules for the allowed string nets. Any questions? Okay, so please interrupt me if there are questions. So now I can define the stringnet Hilbert space. So the Hilbert space is basically going to correspond to each of these configurations and correspond to a different state in our Hilbert space. And so in particular, each configuration, an orthonormal basis for our Hilbert space is given by these different configurations. And to be clear, different geometric configurations are orthogonal states. So, I mean, just to be really clear, this is a different state from, that, okay? It matters what the picture looks like, and it matters where it is in space. So every possible graph that you draw in space is a different orthogonal state. Now, if you're bothered by like a huge infinity of states, you should think of these as living on some underlying lattice. And for example, the honeycomb lattice. In particular, when we draw the actual lattice models, these will be living on the honeycomb lattice. So there'll be more regulated number of states. But for the moment, I'll think of them as in the continuum. And we have this just enormously huge Hilbert space spanned by all the possible sort of planar graphs that we can draw that obey these conditions. And that's going to be our Hilbert space. Okay, so so once we have the Hilbert space, then I can start to talk about building a model, an actual quantum mechanical model. And to build the model, usually you would write down a Hamiltonian and then you'd find its ground state. But we're actually going to go in the reverse order. We're going to first construct a ground state wave function that's defined in this Hilbert space I've written here. And then we'll find a Hamiltonian for which it has that ground state as that realizes that wave function as its ground state. So we'll call that a parent Hamiltonian. And yeah, it turns out it's sort of natural to do it in this order, as you'll see. So first, we're going to just try to write down a wave function. Now, this wave function is a kind of complicated thing to write down because it's going to be a wave function for every possible graph you draw on the plane, obeying those constraints. It has to give you a complex number. So how do you write down a wave function like that? So the way we'll write it down is, that's what I'm going to talk about now, constructing wave functions. The way I'm going to write it down is we're going to, instead of writing down an explicit formula for the wave function, like this wave function has this amplitude for this configuration, we're going to define it implicitly in terms of local constraints. So we're going to write down some constraints on this wave function phi that will uniquely specify phi. Okay, but they don't give you an explicit formula for phi. This is actually pretty important because, well, for many reasons. In fact, some of these wave functions we'll write down is no closed form expression. So it probably is hopeless to try to write down a formula for the wave function. Okay, so what are the rules that are going to define, or the constraint equations which are going to define our wave function? So there are a bunch of them. So let me just show them all and then I'll go through them. So there are, I guess, 5 of them. And there's some various constants that are going to appear in these equations. These are complex numbers that are specified by 6 string types. And F tilde is another set of complex numbers, and Y is another set of complex numbers. So these are going to be some parameters, and you set these parameters, and then it's going to specify, then these rules are going to specify your wave function. So let me go through these rules so you know what they mean. The first one's the easiest probably to understand. This is just a schematic rule. This just says the wave function is invariant under continuous deformations of our string nets, as long as they, always obey the constraints. So if I take this if I take a straight line and I bend it, so what does this mean? This means take a string net somewhere and replace the straight line with a bent line, and you'll get the same number. The amplitude is invariant under that. This is just schematic, but it says anywhere in the diagram you're allowed to make like a little deformation to those lines, and as long as it's a legal deformation, the amplitude stays the same. Okay, so it's sort of topologically invariant up to this, these various constraints about how you're supposed to draw your diagrams. So that's the first rule. The second rule, which is maybe the most important one, is like a reconnection rule. It's sometimes people call this the F move. It says, and if anywhere in your diagram you see this kind of tree-like structure here, you can reconnect these ABCs this other way. So there's an alternate way to reconnect them. You can replace this picture with this picture, but it comes at a cost. To do that, the amplitude of this is a linear combination of the amplitude of this with these coefficients out front, and you sum over all the possible values of f. So when you reconnect this, in general, there may be multiple possible. So what are the allowed f's here? To be clear, these would be all the possible f's that obey those branching rule constraints. B, C, A, and D are fixed. So there's only certain f's that you can draw, certain string types f that would be allowed. And so this would sum over all those possible possibilities and with some coefficient f, which is given to you. And so this is a rule. If you know this, using this rule, I can then calculate the amplitude of this diagram in terms of the amplitudes of these related diagrams, where I've made this local change. I've replaced this tree with this other tree. I'll do an example in a second so you see how this works. This second constraint equation is similar, but it's just upside down. So you have this upside down tree, and to calculate the amplitude, it's related to the amplitude of this other tree, again, via some constants, F tilde. The fourth rule here says, again, it says if I have 2 vertical lines, I can replace it with this, what is this? This I-type structure, whatever you want to call it, again, up to some coefficients. And again, I have to sum over all the possible vertical lines you can draw here. And then the final one says if I have a bubble, whoops, there's a delay here. What's going on? It says if I have a bubble like this, I can get rid of this bubble. And again, it's up to some constant y. And this delta is very important here. This is something like what we call the no tadpole rule. So it says if C and D are different from one another, then the amplitude is just 0. And if C and D are the same, then the amplitude, you can get rid of the bubble and it comes at some cost of some factor y ABC. So these rules, there are some linear equations that determine the wave function. And as I said, there's some parameters you have to input, the values of these f's and these y's. Okay, and
question.
Yeah.
So I guess I can construct an example of this by picking a random group, and then the set A, B, C, D, etc. will be the labels of their representations of the group.
That's one example, yeah.
My question, so this is obviously an example. My question is whether this is the only example.
No.
Namely, whether everything like this that you're going to write down, there will necessarily be a group, perhaps more than one group, such as this is not the case.
Not the case. So I'll explain this in a moment, or maybe not in a moment, but later. But indeed, one example is you can give ABCs to be group representations. You can also be group elements, actually. They could be group elements or group representations. Those are two examples. They both give you some gauge theory. You can also do something called twisted. You can use the cohomology.
Sorry,
kind of
group element or group or conjugacy classes?
Group elements, actually.
Group elements, not conjugacy.
Yeah. So you can do group elements, you can do group representations. Those both give you gauge theory. You can make F, you can choose F in usually you would choose F equals to 1. Well, at least if you choose group elements. But you can choose F to not be 1, you can construct what are called twisted models or Dijkgraaf-Witten models.
I don't see that. So if in the case of group theory, so imagine the group is SU2 and the labels are the various J's, there's an infinite set of them, then these F's are the 6 J symbols.
Yes, that's right.
But then they're not 1.
But the upshot, yeah, that's right. That's if you use representations. Sorry, I'm saying too many things. If you use representations, they're the 6 J symbols. If you use group elements, they're just 1. There are a bunch of different examples that are all related to group theory. However, there are also examples that have nothing to do with group theory. So for example, there's something called a Fibonacci model that gives you something at some non-abelian anyons with a Fibonacci branching rule. So there are many examples. There are examples that we know that that are related to Chern-Simons theory. There are examples that are related to gauge theory. And then there's some examples where, as far as I know, no one knows how to relate them to any field theory, as far as I know. But anyway.
I mean, any group theory, not...
Well, there are many examples that don't relate to gauge theory, but there are even some examples that
just groups. I'm surprised because this is very similar to a topic in category theory, where you can think of the group using this algebra of the representations.
Maybe we can come back to it when I discuss the generality of the model.
I'm sorry about that.
But the short answer is it's beyond groups only are some subset of the known examples. Okay.
Do you also get models with a chiral central charge?
No. Chiral central charge is always 0. So I'll say that too. Yeah, sorry. Yeah.
Thanks.
Michael, could I just ask for a clarification? So since the F symbols are also often used in the unitary modular tensor categories, could you explain perhaps the differences? So here, since there's a planar graphs, I cannot pass one line sort of under or over the other. So there is no concept of braiding, is there?
That's right. So actually, the mathematical structure that is coming in here is a fusion category. A fusion category just has a notion of fusion. It doesn't have a notion of braiding. And so in particular, many of these examples, there is no consistent way to define a braiding. So the mathematical structure here is only, it's only something that describes particles in one dimension where you can fuse them together. And that's why we have planar graphs. And that's why there's no braiding.
I see. So there is no R symbols in this language.
There's no R symbol. That's right.
See. And if the purported purpose of the stringnets is to describe sort of the anyonic models, which on the other hand could be described by this unitary tensor modular, UMCs, how could you establish the relation between the two? In other words, is the
so the input is a fusion category, but the output is a unitary modular tensor category. So the output is a quantum mechanical model, and every quantum mechanical model with a gap defines a unitary modular tensor category. So in a very physical way, the output of this construction includes braiding, but the input does not. The input is just describing fusion. Yes, that's the short answer of what's happening. So there's some input data that builds a model, and then the model has more complex structure, including braiding, that comes out.
Thanks.
Okay, so now I need to mention something called the null string, which I haven't talked about up till now. So in these equations, and basically from now on, I'm going to kind of add one more string type to the set of string types we've been talking about. And this is what we call the null string. And I'll denote it by 0 typically. So what is the null string? Basically, a null string is kind of equivalent to having no string at all. So in particular, so it's equivalent to having no string at all. And so in all of those equations that I've written down, you can let those labels, these labels here can go over all the labels I wrote down plus the null string, so that each of these equations I can make, for example, this E could just be the null string, so I could just erase it if I want. And it describes some rule for how I take, and if I erase it, this becomes like a bivalent vertex here. Of course, B would have to be equal to A bar in that case. But the point is that each of these equations is actually many equations, if you like to think about that way, because if you let one of those labels be the null string, it's describing some slightly different looking picture. Now, null strings, because they're no strings at all, they can be erased and added without affecting the state. So these are, you can think of them almost as a bookkeeping device. They're not really, unlike the regular strings, where the regular strings really are defining the state in your Hilbert space. Like if you move them a little bit, you get an orthogonal state. The null string is not like that. You can erase it, it's the same state. So let me give you an example. So this picture here with this null string is the same thing as the picture. These are the same state. So you can just erase this. It's just a bookkeeping device. And I should say I'll denote it by a dashed line. Okay, so here's another example over here. So here I have a null string. And again, I could just erase it, right? And so this is a trivalent vertex with a null string. I can equivalently think of it as a bivalent vertex with no null string. And then here's just a final example. Here's some diagram with lots of null strings in it, and it's equivalent to this. These are the same state, okay? So this is just something to keep in mind. From now on, we have this null string. And in answer to Subir's question about the Torah code, once you include the null string, the Torah code has two string types, the null string type and then that non-trivial string type. Okay, so now what's the point of these? Now, the key point about these local rules is that they uniquely specify the wave function. So maybe it's not immediately obvious, but given any diagram, no matter how complicated, you can always kind of compute its amplitude, because you can use these local rules to reduce the diagram to simpler and simpler diagrams. And then eventually reduce it to what's called a vacuum diagram, where there's no strings at all. And so in this way, you can calculate the amplitude of any diagram, and in particular, it completely determines phi. So let me give you an example. So let's suppose we wanted to calculate the amplitude of this diagram. So this one. So what am I going to do? So the first thing I'm going to do is use this F move. I can use this F move. If I zero in over here, you can see it has that branching tree-like structure. And so I can use an F move to write this as phi. So let me redraw it like that. So what I did there and there's going to be a coefficient out front, which I'll write, which is going to be f of, let's see, I guess it's going to be ABC. And then I'm going to have 0 C bar. Let's see, 0 C bar, I think C. No, 0 C bar A bar, sorry. I do something wrong here. Sorry, I think I did something wrong. 1 second. Oh, no, this is wrong. This picture is wrong, sorry. Sorry, so this is supposed to be a C, and this is supposed to be, yeah, sorry, I should have prepared this. I did something wrong. Let's see.
Is it A on both? A on the right?
Yeah, this is an A. You mean A on the left, right? I think this should be an A, right? That's where I messed up.
Both A and A bar.
Yeah, sorry. This should be A bar, and this is A. Yeah, sorry. So it's A, B, C, and then it goes 0 C bar A bar. Yeah, okay, I think that's right. Okay, so what did I do here? Whoops. Yeah, I just applied an F move on this little tree here. So I reconnected this thing to this here, right? And it came to this factor of ABC. ABC are the top 3 ABC here. And so it comes with this factor of F. And then I can reduce it further. Now I can use, so let's see, I have F, ABC.
A quick question.
Yeah.
It looks like you converted oh, no, I see. Okay, so the C bar over here is being converted to an A, and this is just an A on both sides. Sorry.
Yeah, I think, okay, let me draw. What I'm doing is converting this to this, and that lower part of that lower half of the picture, right? Like, so did I do that right? So I converted this, and this is all ABC to ABC. And in the initial picture, I had a C bar here. And in the final picture, I have an A bar here. Yeah, so that's what I did. Is it clear in this first step? Okay, then in the next step, I have this bubble here. You can see this bubble, and so I can sort of pop the bubble, and that gives me a factor of Y. So that gives me a Y, and now I have to remember my notation. I think I put the B and C's on the top. Maybe I can check. So I get this factor times phi of this graph. Okay, so I just popped this bubble with the B and C. And then finally I can, this last one is, you can think of this as a bubble again, but with the null string coming out, right? So this again, I can use that popping the bubble thing to get rid of that and write this as, gives me another Y factor, but now it's a Y factor that's just A bar 0, because this bubble, this is a 0 here, right? So this is just another bubble, a particular kind of bubble where the exterior string is a 0, and I can get rid of it, and now I'll have phi of just the null string. But the null string is just the same thing as the vacuum, so I'm just going to write phi of the vacuum here. So I've gotten rid of all the strings. Okay, you can see a key point here is that you can erase these null strings. So because you can erase null strings, you can start off with a complicated diagram and eventually end up with just nothing. And then phi of the vacuum will just set to be 1. It's just a normalization. Okay, and so then that tells me the value of my original diagram. Maybe it's not obvious, but with any stringnet diagram, you can do this. You actually can convince yourself. There's an algorithm for doing this, for taking an arbitrary diagram and gradually reducing it down to nothing. And you're going to get factors of F's and Y's and things like that. Any questions about this?
I have a question here. So usually this f and y's, they are subject to some ambiguities or redundancy in the fusion category, right? So it could be that two sets of f and y's corresponds to the same fusion category, even though their values.
Yeah, I'm not going to say a lot about that here, but there's something like so there's I think what you're talking about is different. There are some gauge transformations you can do on f and y, which will give you the same physical phase, but they may give you a different wave function, but they'll give you the same phase. Indeed, that's true. So yeah, that's right. So that's correct. I'm not going to say much about that here, but what that means in practice is that if you want, and in fact, it's not a one-to-one construction, basically. There are many f's and y's that can give you the same phase. That's generally true, actually. Even if you get rid of the gauge redundancy, there's additional redundancies that can happen where I could say more about that, but yeah.
Michael, may I ask for, you already mentioned several times the example of the Torah Code. So they have, and again, this is just maybe a different way of looking at this, but I would naively imagine that there are two kinds of strings, the ones that join E to E particle and M to M. And, you know, in the Torah Code, that would be physically different string operators, different product of sigma x's and sigma z's.
No,
right?
so it isn't E and M. So it isn't E and M. So the string types in the Torah Code are just, they correspond to, I debated whether I should introduce the Torah Code. I didn't think I had time to explain a string picture for the Torah Code. But if you look at the Torah Code wave function in, say, the sigma x basis, for example, and you say when sigma x equals -1, you say there's a string on the link. And when sigma x equals +1, you say no string. Okay, then what you get is this picture where the Torah Code is made up of like closed loops, you know, on your lattice, whatever your lattice is. Like maybe it's the square lattice or the Hahn lattice. And the wave function is the superposition of all possible closed loops, okay? So each of these closed loop configurations, those are a stringnet configuration. And you can see that in this particular case, there's only one non-trivial string. There's kind of, you can either have a string or no string.
You don't have to,
and so that's how it maps over. So these diagrams I'm drawing here, these are not E's and M's. Like the quasi-particle excitations are the next layer of analyzing the model. This is just describing the Hilbert space, the degrees of freedom. So in the Torah Code, there are only 2 degrees of freedom on each link. There aren't 4 degrees of freedom. Although there are 4 quasi-particle types, there are only 2 degrees of freedom on each link. So these strings that we're talking about are really just the degrees of freedom on each link. They're not the excitations.
I see. And I do not need to introduce the, for instance, the product of sigma z's as an example of a string?
No. Those are operators. So those are string operators that are going to act on some space. Right now, I'm just writing down the original, the Hilbert space and the Hamiltonian. Then there's a next layer of analysis, which I'm probably not going to get to, which is how you construct the operators that are going to act, that are going to create excitations. Okay, so now I'm just writing down the ground state wave function. In the case of the Torah Code, that ground state wave function is just phi equals 1. It's very simple. It's all possible closed loops. They all have the same amplitude 1, right? The F is just 1, the Y is just 1. Everything is 1 in the Torah Code, and it's just and there's no E and M string or anything like that yet. We're just writing down the ground state wave function, which in the Torah Code case is just 1. It's a uniform superposition of all possible closed loops.
Gotcha. Thank you so much. That clarifies it a lot.
Yeah. So in effect, these local rules are a trick for writing down complicated wave functions. Wave functions that could be very hard to write out explicitly or maybe impossible to write down explicitly, we can define through these local rules. But of course, there's a problem, which is that the rules are not generally self-consistent. So here's a way where they could not, here's maybe the most important way where they may not be self-consistent. So you may have some diagram like that. I have left off the labels, but a diagram that looks like this, and you can reduce it to a diagram that looks like this in 2 different ways. You can use 2 F moves to go along this upper path, or you can use 3 F moves to go along the lower path. And these are 2 different ways you can relate this diagram 1 to diagram 2. And in general, if you choose your F in some generic way, the coefficients that appear when you do that relation won't be the same. So this product of these 2 Fs won't be the same as the product of these 3 Fs. And then that means there's no solution to those rules. There's no self-consistent solution, right? So you have to pick your F's and Y's to obey very special properties for the rules to be self-consistent. Okay. In general, maybe another way of saying it is, in general, these rules have zero solutions to them. There's no solutions. You have to pick them very specially so that you get one solution. Okay, so here's self-consistency conditions. So it turns out there are 4 conditions. They're both basically necessary and sufficient for these rules to be self-consistent. The first one I've already basically introduced. It's called the Pentagon Identity. F has to obey this nonlinear equation to get self-consistency with respect to that diagram. The other ones I won't explain here, but they're not hard to derive. This is some relation between F tilde and F, which is the two diagrams that differed by this kind of reflection. This is some rule. This is actually easy to derive. This just sort of says when one of the null strings is 0, you can just erase it. It's related to that. So the F move is always trivial when one of these upper strings is the null string. And similarly, this 4 is easy to understand. So it's easy to show these conditions are necessary for it to be self-consistent. But actually, what's much harder is to prove they're sufficient. But that is the case. So these conditions, if they are obeyed, you have exactly one solution to those equations. There's in particular, there's always at least one. There's always, the crucial thing is there's always the rules are, there's always at least one solution if these rules are obeyed. Because the fact that there's at most one solution that's generally the case, no matter how you choose F and Y.
Michael, can I ask a question? So you require anything like unitarity in this formulation?
No, not yet. That's next slide.
Okay.
So you don't need unitarity for this. F doesn't have to be unitary for the wave function, for those rules to be self-consistent. However, that's what my next slide is. If you want more than just a wave function, if you want a Hermitian parent Hamiltonian, then you need some extra conditions. At least, let's put it this way, at least the way that we construct the parent Hamiltonian, we need some extra conditions for it to work. And so what are those extra conditions? Well, these are these next 4 ones. And the most important of these you just mentioned is that F has to be unitary. So for each choice of A, B, C, and D, you can think of F as a matrix that describes like this reconnection. So it's a matrix defined by the two other labels. And that matrix has to be a unitary matrix. That's what this equation says. So that's one condition. And then there's a couple other conditions. This is, I have to say what D is in a second. D is this absolute value of Y0. What D really is it's the amplitude for this graph. So it's the Y00 is the amplitude for this loop. And so D is the absolute value of the amplitude for a loop. We call that the quantum dimension. And that appears in these conditions. So there's, in this one here, F has to be, the absolute value of F has to be equal to this expression, the absolute value of Y has to be equal to these expressions, and so on. So the claim is, as long as these extra 4 conditions are satisfied, we can construct a Hermitian parent Hamiltonian, H. And so, that's where unitarity comes in. That's condition 3 here, or condition 5 here. In order to guarantee its Hermitian, we have to impose this extra condition. Okay, so.
Excuse me.
So that now,
Sorry, so the 5th condition you say is about the unitarity, the 5th condition. And here the statement, the previous setup, you said that if we only have the previous condition, we cannot guarantee the Hermitian parent Hamiltonian, but we still can write down some wave functions living in the Hilbert space. But then
that's right.
If I don't have this condition written from 5 to the 8, then can I still have some Hamiltonian, which is not Hermitian? What does it mean? Does it mean that wave function decay of the state will not unitary?
Yeah, so if you have a solution to the first 4, but not the last 4, you can write down, so we have examples of this. I mean, certainly you can write down a wave function, and you can also write down a non-Hermitian Hamiltonian which has it's as a eigenstate or something. But in practice, what it means is that wave function, at least in certain examples, I don't know if I can prove it's always the case, but in many examples where you violate this condition here, you find that wave function does not have zero correlation length. Okay, it might even be, I'm not sure, it might even have it might even have algebraic correlations, but it certainly doesn't have zero correlation length. And so then, because it doesn't have a zero correlation length, it's probably hopeless to construct a Hermitian commuting projector Hamiltonian. So these conditions are really important if you want a Hermitian commuting projector Hamiltonian. It seems very likely. I mean, for example, this condition here, these normalizations of y. Actually, this is a very important one. The normalization of y here. If you don't choose y to be normalized in this particular way, then you can sometimes write down a Hamiltonian, and it might, but to write down a commuting projector Hamiltonian is probably impossible in general, because these wave functions have finite correlation length.
Okay, but it seems you are maybe condition different from the situation different from just Hermitian. It seems like you are describing this phase might not be gapped.
You're saying you're saying if we violate these conditions, what could go, what's the nature of the wave function if you violate these conditions? So there's two possibilities.
Some phase of matter.
Yeah, there's two possibilities. I think there are some cases where the wave function is still gapped, but it has a finite correlation length. I can give you examples like that. There are also examples, these examples I don't know, but I suspect there are examples where it's actually, the wave function has like algebraic correlations. And so it's probably not the gap ground state of any Hamiltonian. So you can have that's the worst case scenario where your wave function is just not describing a gap state of matter. But there are also situations where it is describing gap state of matter, but just not a commuting projector zero correlation length state.
So in principle, when people study, usually impose this condition. Do people maybe use last condition and still explore other phases? That's kind of question I was asking.
Do you ever want to drop these conditions? Is that what you're saying? No, I would say, I mean, there have been people who have thought a little bit about dropping some of these conditions. They've considered models which violate some of these conditions, but it may be interesting to think about. It may be interesting to think about, but it's harder to, well, you need different tools, right? Because they're not going to be ground states of a commuting projector Hamiltonian, so it's harder to attack them, understand what's going on. But people have thought about certain wave functions that violate some of these conditions. Yeah.
So Michael, just one more question about this slide. So like your definition of quantum dimensions, absolute value of this value of the diagram. Yeah. And you also have absolute value in various, the B of 6, 7, which are usually just equal, like if we do diagrams in a modular category with braiding, and where D will be positive. Can you comment on that difference?
Yeah, so we're being a little bit more general. So I didn't go into the gauge transformations, but for example, maybe you're thinking of equation 7 here as an example. Equation 7, you can make this, you can always do a gauge transformation to make this just an equality.
Okay.
And people will often choose that gauge, but there are certain situations where using that gauge actually makes the wave function more complicated. So the double Fermion model is an example. So sometimes it's nice to not force yourself to choose that gauge.
I see. Okay, thank you.
Yeah, I have a question here.
Yeah.
Sorry.
You mentioned that this when there's no unitary condition, you may have a finite correlation length, and maybe still the wave function may still be a gapped ground state of some Hermitian Hamiltonian. Whether there's an example of this, you said.
Yeah, I think that you can do. It's basically you can take any stringnet wave function and any one that obeys these conditions, and then you can do a transformation where you add for every vertex ABC, you multiply your wave function by some lambda ABC, some factor. So you introduce some constants like this.
I see.
And so every time you see a vertex like this.
Yeah. So this non-unitary gauge transformation may violate this, you say?
Yes.
Okay. But okay, let's ignore this one. Besides this, we say they are gauge equivalent, so there's no problem. So which the one violate the unitary condition more fundamental, more intrinsically, which cannot be gauged away.
Oh yeah, there's examples like that too, like the Fibonacci model. If you choose 1 minus √5/2.
Exactly. So those one, do you mean that those one may have a algebraic correlation, maybe gapless? That's what you.
I can't remember the status of that. I believe that Matt Hastings and Michael Friedman studied that. I don't remember if they studied the correlation length. They were arguing that that wave function is always gapless, but I think they argued it based on some other modular transformations or something. But I don't know. It's possible to me that maybe the correlations are themselves algebraic in that state. I'm not sure.
Yeah.
It may be hard to tell without doing numerics because it's, I don't know. Or maybe you can map it onto some known statistical mechanical model or something.
Yeah.
I don't remember the status. I just have some gut feeling that that could happen, maybe, but I don't know.
Okay, thank you.
Yeah. Okay, so what's the situation? So basically, you have these 8 self-consistency conditions, and anytime you can find a solution to them, you get a nice, well-defined wave function phi. And furthermore, this phi, as I'll explain in a second, is going to be a ground state of a nice Hermitian Hamiltonian, commuting projector Hamiltonian. So let me just give one very crude example, so that maybe the first kind of an interesting and very simple example is the so-called Fibonacci model. So in that model, there's 2 string types. Here I'm including the null string type. So there's 0 and 1. And the dual string types are just the simple one. 0 bar equals 0, 1 bar equals 1. The branching rules are the ones I've written here. Basically, the easiest way to say it is the diagrams look like this. So I leave them unlabeled because there's only one non-trivial string type. So the diagrams are just basically arbitrary trivalent graphs. I mean, well, subject to those no vertical bending rules. And so this would be like a typical Stringnet picture. So for each one of these diagrams, we want to write down a wave function that will give us some complex number. So how do we do that? So here are the local rules. So instead of telling you what f and y, I could tell you what f tilde and y are for this model, but it's just not so illuminating. So instead, I'll just write down explicitly what the rules look like if you substitute the f's and y's into those equations. And so the rules look like this. Whoops. So tau here is the golden ratio, 1 plus √5/2. It appears in this model, in the f's and the y's. And here are some of the local rules. So here's like the reconnection rule. And this is these are 2 kind of reconnection rules. This is the like 2 vertical lines being smushed together rule. This is the popping the bubbles rules. And this is the no tadpole rule that says you can't, whoops, I should have drawn that the other way. Which says that, you can't have a tadpole. And these rules, again, they uniquely determine the wave function. So you can calculate the wave function of any diagram with them, and it's quite complicated. In fact, it's pretty likely there's no closed form expression for these wave functions. Yeah, tau appears in here because I guess I should say that the solutions to these self-consistency conditions are extremely sparse. They have a lot of structure. And so if you just put in these branching rules, the ones I've written here, and you just try to find all possible solutions to those self-consistency conditions, you only find 2 solutions. One which looks like this, and the other where you put a minus sign, 1 minus √5. And that second solution doesn't obey the hermiticity condition. So if you want to obey all the conditions, this is the only solution. Okay, so this describes some interesting model. I'll say in a moment, a little bit later, what the nature of this Stringnet model is. But at the moment, it defines the wave function on these diagrams, on these Stringnet configurations. Okay, so Now, maybe I can say a little bit about the Hamiltonians, how you write down So far, I've told you how to write down wave functions. Now, how do we write down the Hamiltonians? So the models we're going to be thinking about, they're going to be spin models where the spins live on the links of the honeycomb lattice. And I'm orienting it this way so that, well, it's because of this no vertical bending rule. I want all the pictures to look kind of like valid pictures. And let's see, each one of these dots is supposed to be a spin. I put a spin in quotes because it's not just like a two-state, it's not like a spin 1/2. It has some large number of states. In general, it can be in these states A, B, C, one state for every string type. Including the null string. So in the Torah code case, we would have one or two types. And so each of our spins would have two states, just like in the usual Torah code you're familiar with. And now each of these spin states, I label them A, B, and C. I label them by string types because I want you to think of them as strings. So there's a kind of language for thinking about the states in this Hilbert space. If a spin is in state A, we'll think of that link as occupied by type A string. And if a spin is in state 0, we'll think of it as having no string. And so in this way, any spin state on this honeycomb lattice, at least in this basis, corresponds to some valid, it doesn't necessarily obey the branching rules, but a valid stringnet configuration. Okay, so now what's the Hamiltonian? So the Hamiltonian is going to have two terms, Q, V, and Bp. So V is supposed to be vertex. So for every vertex in this picture, we're going to have a QV, and for every plaquette, we're going to have a Bp. And let me now just define how QV and Bp, let me tell you how QV and Bp are defined. So QV acts on 3 spins near a given vertex, and it's defined by these equations here. So let me try, first I need to explain what this delta is. So this delta is just a symbol that summarizes the branching rules. So delta ABC is 1 if this is an allowed triplet, and it's 0 if it's not allowed. And so QV will just project onto states that obey the branching rules, okay? So it gives you 1 if the state obeys the branching rules, and it annihilates states that don't obey the branching rules. And so in particular, this first term here, since there's a minus sign here, it's energetically favored to have states that obey the branching rules. You want to have all the vertices. And so this first term basically guarantees that your ground state is going to be a state made up of valid string nets that obey all the branching rules. Okay, so that's QV is the easy part. Bp is the hard part. So Bp is a term that's on every plaquette, and it has this form. So let's see, a few things to say. So it's a sum. We write it as a sum over these terms. This sum goes over the different string types. It runs over the different string types, and it's a sum of these more basic operators, these BPS operators, which I'll explain what they are in a second, with some coefficient AS. AS is some complex number that you determine this way. So, and each BPS, so it's an operator that acts on a plaquette. It's a 12-spin interaction, if you think about it in terms of spins. It acts on these 6 spins around the plaquette, and also these 6 exterior spins out here. And how does it act? So I'm going to explain how it acts graphically. So the easiest way to understand it is it's actually easier to understand how it acts on a bra than a ket for technical reasons. So how does BPS act on this bra? This is a particular state of 12 spins. So the way to think about it is BPS just adds a type S loop of string in this interior of this plaquette. And then, okay, so that's what I tried to draw here. So BPS just adds this string, and then what? Then what you do is you take this diagram, and then you just think of this as like a diagram you want to evaluate the amplitude of. And so using those rules, you can kind of fuse this string onto onto these edges out here using the local rules. And so eventually, after you fuse it on, I could show you, it takes about 5 steps. You can reduce the diagram to something like this. Okay, and what's happened when I fuse it on is H changes to H prime, I changes to I prime, J changes to J prime. So all of these interior spins change their state. The exterior ones don't get affected, but the interior ones change their state. And so in the end, you're going to get a sum over all these, the values, possible values of these edges. And there'll be some constants. These are like the matrix elements, and they'll come about, there'll be products of F's and Y's that you get when you fuse these things on. And you can work out what this constant looks like. It's a kind of horrendous mess. So I'm not even going to write down the indices, but it has this structure. At least the way we've set things up, you can write it this way. It's a product of 8 F's and 7 Y's or something. And so you can write out an explicit formula, but the best way to understand it is this way, that it's really just adding a type S loop of string. And then you just fuse it on there to determine what the matrix elements are. Okay, so
Michael,
so that's it. So that's how we define our 2 operators. Our QV operators obeys the branching rule. Our BP operator kind of creates fluctuations. It adds these type S, these strings, which gives you off-diagonal matrix elements, which are changing H to H prime.
Hi,
okay,
Michael.
so now let me just, yeah.
May I ask a quick question? So sure. We can argue that B scores to BP, so by doing diagrammatics, but is it easy to show that BP itself is Hermitian?
What was the is it easy to show it's Hermitian? So
yeah,
it's not that,
or does it depend on gauge? Sometimes it may look non-Hermitian in some gauge, but Hermitian in some other gauge.
So if your F's and Y's obey all those conditions that I wrote down, in particular conditions 5 through 8, then you can show that this BP operator is Hermitian.
I see. Okay, thank you.
Okay, so what are the properties of this Hamiltonian? So the first property, most important property, is that these operators QV and BP, they all commute and they are Hermitian. The fact that probably the most non-trivial ones, it's easy to see the QVs commute with each other because they're all diagonal on the same basis. And it's also easy to see the QVs commute with the BPs because I didn't say this, but the BPs by definition, their matrix elements are 0 unless both the initial and final configuration obey the branching rules. And so it kind of by construction, BP commutes with these projectors onto the states that obey the branching rules. So it's easy to see they commute with each other. The hard thing is to show the BPs commute with each other and to show that they're Hermitian. But one can check that. One can explicitly check that they commute, just it's some algebra. There's also alternative arguments for why they commute, but anyway, one can show that. The next property is that these are projection operators. So they have eigenvalues 0 and 1. Again, you can check. It's easy to see QV as a projection. It takes a little more work to see the BP as a projection. And by the way, the fact that it's a projection depends on those coefficients A sub S having particular values. So if you chose those coefficients A sub S in a different way, it would still obey this first condition, but they wouldn't be a projection operator. Third property is that if you define this model in kind of a disk, so you take just like a chunk of honeycomb lattice and just like that has a disk-like structure, you can show that there's a unique state. So since these commute and are Hermitian, you can simultaneously diagonalize them. And so then the only question becomes, what are the allowed values of their simultaneous eigenvalues? And you can show that in a disk geometry, there's a unique state which has QV equals BP equals 1. And so since there's a unique state, that's the lowest possible energy you could have because it saturates all the projectors. And so that means that that this Hamiltonian we've written down has a unique gapped ground state. And the gap is just 1, I guess, because the lowest, or at least 1, because you have to violate at least one of these projectors to, they're projectors. So their eigenvalues are discrete, 0 or 1. So there's a unique gap ground state which obeys this condition. And then the final thing one can check, which is nice, which is that this ground state wave function, it's a wave function defined on the lattice, but you can show that it's the same as that continuum wave function that I defined via the local rules. More precisely, it's the same thing as the continuum wave function, just restricted to the lattice. So we've really realized this Hamiltonian is a true parent Hamiltonian for that wave function, at least when put on the lattice. Okay, so let me just say a few words about this example, this Fibonacci model. So how would the Fibonacci model work? Just to be concrete. So there we have two string types, 0 and 1, the null string and the non-trivial string. And so we would have a spin 1/2 model. Each one of these spins would be a spin 1/2. And what would the QV operator look like? That's the easy one to write down. So it would project onto these configurations. So you're allowed to have 0, 0, 0. That means no strings coming in. You're allowed to have 1, 1, 0. That means kind of a closed a string coming in and coming out. And you're also allowed to have 1, 1, 1. But you're not allowed to have 1, 0, 0. That's like a single string coming in and just ending. So QV would project onto these kinds of states and will give you 0 when acting on this kind of state. So it's some 3-spin interaction. You could write it down that has these properties. You could also write down BP, which is a 12-spin interaction involving spin 1/2, and you could write it in terms of Pauli matrices if you wanted to, but it's not that illuminating, so I won't write it down. So then what is the properties of this model? So it realizes something called the double, well, we could call it the doubled Fibonacci phase. It's a topological phase which has 4 anyons, which I've called one. One is now my name for the trivial anyon. Phi is some non-trivial anyon I'll tell you about. Phi opposite phi OP is another non-trivial anyon. And phi times phi opposite is the composite, if you fuse these two together. So what are the properties of these anyons? So phi is a non-abelian Fibonacci anyon that obeys these kinds of fusion rules. So you fuse it with itself and you gets 2 possible outcomes, either the vacuum or itself. And phi opposite has the same kind of fusion rules, but its braiding statistics are opposite. So it's like the time reversed partner. So one way to think about this double Fibonacci phase is a little bit like a topological insulator. Think of it as a bilayer of some Fibonacci topological phase and its time reversed partner. The Fibonacci phase has only 2 anyons, 1 and phi, and the time reverse partner has 2 anyons, 1 and phi opposite. And then the doubled phase has, well, it has all 4 possibilities that you can get from these two layers. Okay, so now let me talk a little bit about what phases can be realized by these models, just more generally.
Michael,
so this was,
if I may ask a question here. So I did remember you mentioned that in Stringnet models, you cannot get a chiral central charge. Probably this is, looking at this slide probably means, by construction, your Stringnet model always have some sort of a time reversal symmetry. And if yes,
no,
no,
it doesn't. Yeah, so that's, I think in our original paper, so I'll say a little bit about this. In the original construction, we more or less assumed time reversal symmetry. And so all the models we wrote down were time reversal symmetric. But this more general construction we're talking about here does not need to be time reversal symmetric. And so there are examples. I can think of concrete examples where you have Stringnet models which are not consistent. They're incompatible. Not only are the model itself not time reversal invariant, even the anyon content is inconsistent with time reversal symmetry.
I see. So yet still you have to have a 0 chiral central charge.
That's right. So I'll say about that in a slide or two why you need that.
Okay, thanks.
Michael,
okay,
sorry, not to slow you down.
Yeah.
Could you explain just very quickly how do you derive, or where does the diffusion rule phi times phi equal 1 plus phi? How can I see it from the language of the string nets? Is it easy?
It's not easy. I have some slides on anyon excitations, but I don't think I'm going to get to them. They might partially answer your question, but I don't know if I'll get to them. Yeah, it's not easy. You have to do some work to calculate it's a non-trivial calculation to go from this, well, the way we do it is very physical. We take a Hamiltonian and just try to construct the excitations. But so that's one approach, and it's non-trivial. You have to do some work. There's also a kind of direct mathematical approach, which is called the Drinfeld center or something, where you take this data and you just calculate the anyons from that data. Again, my impression is that's a non-trivial calculation to do. So it's non-trivial to go from this input data to the full data of all the excitations in general. I mean, there's an algorithm. I think in principle we know how to do it, but I don't know in practice that one can really do it very easily.
Is there an easy way to know by looking at the Stringnet model whether or not the anyons are abelian at least?
Yes, I think that one can, there's necessary conditions for it to be, let's see. Yes, I think that's right. Yeah, you need abelian fusion rules. So abelian branching rules. So I could say what that means in a second, but it basically means for any two incoming strings, there's a unique outcoming string type, and it's also symmetric. So like if you have an A and a B, like so for any given A and B, there's a unique C, and furthermore, it's the same, the same branching rules. Whether so I didn't say I emphasize this, but these branching rules don't have to be symmetric with respect to left and right. But if you want it to be abelian, they should be symmetric, I think.
Fantastic. Thank you so much.
Okay, so
Michael, by the way, you shouldn't feel constrained about the time limit. You can just finish everything you prepared. So take your time.
Okay. Okay, so where was I? Oh yeah, so I was going to say what phases can be realized by these models. So let me just say a few words about that. So I'll give you some examples and then I'll tell you the general statement. So one kind of example, which is basically this double Fibonacci example, is you can realize every topological phase of this form, T cross T opposite. So any bilayer type thing. And yeah, I could say a few words about that, but basically to realize a phase like this, you let your string types be the anyon types in, let's say, T. So you have one string type for every anyon type in T, and you let your branching rules be the fusion rules in T, and your F symbol to be the F symbol in T. So you just input all the fusion data coming from T, like the anyon types and their fusion rules and F symbols, and then the output is T cross T opposite. So that's actually this Fibonacci example. Maybe that would have been an easy way to answer your question, Andre, which is that this particular data you can check is the F symbol for the Fibonacci phase. And so then you know that if you input the data for the Fibonacci phase, you will get the doubled Fibonacci phase out of this construction. That's something that's known. So this is one kind of thing you can get. It's like doubled, what we call doubled topological phases. The other thing you can get is, which Nadi was mentioning, is you can get any gauge theory with a finite gauge group. These are called quantum double models. You can get those by making your string types either the group elements in G or the group representations. Those are two different ways to get the same thing. Another thing you can get is what are called Dycroft-Witten theories, or sometimes called twisted quantum double models. And these, again, here you would make your string types group elements, but your F symbol would be this so-called cocycle. Instead of, in this case, your F symbol is just 1 if you're using the group element construction, but here your F symbol would be cocycle. So that gives you Dycroft-Witten theory. By the way, I should say the Torah code is a special case of number 2, just to be clear. Now, what's the most general statement? So the most general statement, as far as I understand it, is that these models, we know they can realize any.
I'm sorry, can you clarify that a little bit? So the Torah code has, so I understand why at low energies the two systems are the same. When you say the Torah code is a special case, but is it clear that the excited states are also the same? Or
of which two cases? Representations and group elements? Is that what you're talking about? The two different.
You said that you gave the example of the Torah code using the group Z2. I understand why at zero energy, they are the same. I understand why the topological data is the same. But are you also claiming that all the excited states of the Hamiltonian are the same or not?
Wait, so when you say same, which two things are you comparing?
Number one is the Torah Code. It's a well-defined Hamiltonian.
Yes.
Number two is your construction based on the group V2.
Yes, okay, thank you.
I understand why at zero energy they are the same. I understand why the anyon types, braiding, etc., are the same. I'm asking whether the whole spectrum of the Hamiltonian.
Gotcha. Not, yeah, it wouldn't be the same. No, because the particular way we define our Hamiltonian, it's kind of a variant of the Torah code. It's not the usual Torah code. So yes, it's not the same as the usual Torah code, but it has the same ground state as the usual Torah code, and it's in the same phase as the usual Torah code. But indeed, it's not exactly the same Hamiltonian, and it doesn't have exactly the same eigenvalue spectrum.
Okay, and the third thing you have here is Dyrkop-Witten, but you can also think of the Z2 gauge theory. If you just constrain all the local field strength to be trivial, which is the same as restricting to low energies. In fact, this is what Dyrkop and Witten do in their paper. They constrain the product around each triangle to be trivial. Is your model similar to this, or is it similar? And then the spectrum of excitations is of course also different. Is your construction similar to this, or is it more similar to the Torah code?
Okay, so let's see. I'm trying to understand what distinction you're drawing. Can you say what the distinction is you have in mind again?
Okay, let's consider the untwisted Dyrkop-Witten theory. This is a mouthful for something that is known. But just, I mentioned it this way only so that we're completely on the same page. This theory does not have the excitations. You can introduce the anyons as defects, but it does not have any non-trivial excitations because every triangle is constrained to be trivial. That's not the same as the Torah code. It's closely related, but it's not the same.
Yeah. No, what I have in mind is more like the Torah code. So when I say Dyrkop-Witten theory, I'm thinking more along the analog of Dyrkop-Witten theory, but for Torah code. So it contains all excitations are kind of, it's a local model. Maybe that's another way to say it, right? It's a Hamiltonian with local tensor product Hilbert space. I don't put in any constraints. There's no Gauss law constraint. There's no zero flux constraint, right? You can put them in energetically, but they're not constraints.
But then it's not the same as Dyrkop-Witten theory. You said the Dyrkop-Witten theory is sorry. You said the Dyrkop-Witten theory is a special case of what you do.
Okay, maybe I'm abusing the terminology, but there's something extremely close to Dyrkop-Witten theory that you can make with a Torah code-like model. That's what this is a generalization of.
Yeah, but that's not what is being discussed in the Dyrkop-Witten paper.
Okay.
But low energy topological field theory are the same.
No, of course. No, I'm not disputing that. At low energies, all these constructions are the same. So my first question was about the relation of Torah code to Michael's construction. And at low energies, they are the same. And I asked about the excited states. And then I asked exactly the same question about.
Oh, I see. You're really asking, is it exact? It's definitely not exactly. No. Again,
but it's not even approximate
ground state. Same ground state.
Right. But for the Torah code, you said they're not exactly the same, but they're kind of deformations of each other. For Dyrkop-Witten, they're not even deformations because Dyrkop-Witten theory does not have any of these excited states.
Okay, so maybe I'm using the term in a different way. I mean, maybe you should call it twisted quantum double model instead of Dyrkop-Witten type. But they're very closely related. Okay, they have the same ground state. But okay, maybe it's not literally like. Yeah.
I think Dyrkop-Witten is mostly formulating path integral, but I think Michael is clearly relating the two by the group cohomology co-cycle data.
I don't think this distinction is essential. There is a different question of whether the model does or does not have the excited states. That's a physical distinction. And whether you use one formalism or another is not essential.
But the ground state,
I understand the answer to my question, so I think you should just continue.
Okay. But the ground state, you agree, is the same, right? I mean, they can map one ground state of Dyrkop-Witten theory to the...
No, That's obvious. It's obvious that the ground states are the same. My question was about the excited states.
No problem. Great, thank you.
Okay, so the more general statement and
wait, can I ask a clarifying question? Sorry.
Yeah.
I don't want to belabor this discussion too long, but the first excited state in the Stringnet models and also in Torah Code is like extensively degenerate, right? You like violate one plaquette term or something, and you can do it anywhere, and those will all have the same energy.
Yes.
Okay.
Okay, so what is the general statement about what phases can be realized? So mathematically, the statement is, or at least we know it can realize any of these phases. Probably this is all it can realize, are things called Drinfeld centers. So this is a mathematical instruction. The input to this is this category C is something called a unitary fusion category. It's very similar. A unitary fusion category is very similar to the basic input data Stringnet model. You have some set of objects, you have some fusion rules, those are like the branching rules, you have an F symbol and so on. So given any unitary fusion category, there's a mathematical construction which lets you build some a unitary modular tensor category out of it. And that's called this Drinfeld center. And it's believed, at least, I don't fully understand Drinfeld center construction, but my understanding is Stringnet models basically are some physical realization of that. So the phases we can realize are precisely the ones you get by taking the Drinfeld center of some unitary fusion category. And really the Stringnet model is something where we, as I said, we do this in a physical way. The input data is something like a unitary fusion category, and then the output is a Hamiltonian, and the Hamiltonian, its anyon types are exactly those given by this mathematical construction. Okay, so from a mathematical point of view, you could say we can realize any anyon theory that's the Drinfeld center of a unitary fusion category, but that's not that may not be the most helpful way of characterizing things, because how do you tell whether a given system is the Drinfeld center of another thing? It's not so easy. So it's nice to have a more physical characterization of what phases we can realize. And so here I'd say I'll state as a conjecture, I think we're probably reasonably confident it's right, which is that the phases that can be realized by Stringnet models are precisely those phases that support gapped edges. So that's what this conjecture says. So a topological phase can be realized by Stringnet model if and only if its edge with the vacuum can be fully gapped. Okay, so here's our topological, here's a topological phase, here's a vacuum, its boundary should be gapped. So certain phases like the Torah Code have a gapped boundary. The doubled Fibonacci phase has a gap boundary. All the Stringnet models, they always realize things with gapped boundaries. That's easy to show. But the conjecture is the converse is also true. So any phase that has a gap boundary can be realized by a Stringnet model.
Michael, I have a question, maybe / a comment about this conjecture. So I thought there's a paper last year by Demfried and Telemann. They show that a 2+1D TQFT has a gap boundary if and only if it's a Drinfeld center.
Well, it depends what you mean. So I don't fully know their paper, but they're not starting from this what I would call what a gap boundary means, right? They're starting from some more abstract mathematical structure, and they're saying this is probably the same thing as a gap boundary. And then they're proving if it obeys this property, then it's a Drinfeld center. But what you really want, that's why I made this as a conjecture, is we have a physical meaning for what a gap boundary means, right? Which is like you have a Hamiltonian on a lattice, it has a gap in a unique ground state. So what you really want to show is, any phase that can be realized by a Hamiltonian of a certain type, and that Hamiltonian can be defined in a geometry with a boundary and has a unique gap ground state. Any such phase can be realized, right? And that has not been proven.
But you don't think any such gap boundary realized by an explicit Hamiltonian will flow to a non-trivial boundary discussed by Danfried and Tellerman?
I don't know why it's obvious that should be the case. I think it's very reasonable. That's why I said you can be reasonably confident, but I don't think there's any like very convincing argument for that. Yeah, I don't know. Maybe we can discuss afterwards, but my impression is that it's not obvious. I mean, it's kind of like related to questions about whether, topological phases are described by field theories and things like that. And to me, that's not obvious either. Like, it probably breaks down in higher dimensions. Like, why should it be true in 2 dimensions? I don't know.
Okay, I see.
But anyway, the conjecture, again, I think it's pretty likely to be right. In the abelian case, we have pretty stronger arguments for it, I think, for abelian phases. But for non-abelian phases, I'd say it's a little weaker. But the conjecture is that, it can realize precisely those phases with gapped edges. So what's a corollary of this is that it cannot realize phases with a non-zero chiral central charge, because if you have a non-zero chiral central charge, the boundary is always gapless, right? So if you believe this conjecture, there's no hope. Actually, you don't even need this conjecture. You can probably prove directly. There's no hope of realizing phases with a non-zero chiral central charge. And so in particular, you can't get these chiral phases like a Laughlin state or anything like that. So this is why the chiral central charge comes in. It's not because the models are time reversal symmetric. It's because the models have gap boundaries, and gap boundaries incompatible with a non-zero chiral central charge.
Michael, can I have a question about the corollary? So I guess explicitly in your Hamiltonian, you can just truncate your space at some point, and demanding some conditions on the Q and B, like what we do in the rough and smooth boundary for the Torah code. And then you can probably explicitly show that flows to a gap boundary, and therefore
you don't even have to show it flows. It's just gapped. Yeah, you can show
it's just gapped. Sorry, yeah. And therefore C minus has to be 0. Okay, I see. Thanks.
Yeah, that's right. So that's what I sort of said maybe too quickly here, which is the direction, the only if direction is easy to prove, because you can explicitly construct a gap boundary for stringnet models very easily. It's very natural. The if direction is the harder one, but yeah, we only need the only if direction here. So that's right. So
Michael,
this corollary you derive,
So I have a question. So if you start with a given stringnet lattice Hamiltonian, there are some obvious gap boundary that one can construct, but maybe it's difficult to classify all the gap boundary conditions.
There are many more gap boundaries, and this was something that was addressed in the paper by Kataev and Kong to some extent. So they have a way to, I think, if I understand their paper, they have a way to construct more general gap boundaries for stringnet models. In particular, they claim to get all of them, I think.
I see.
But yeah, they're right. The particular obvious one we're talking about is just one of them.
Right. Okay, thank you.
Yeah. So then maybe one other conjecture, which is just maybe worth stating, which is, and this one is just, I don't think we have, I don't really have that much evidence for, but it seems likely, I don't know, I sort of feel it's probably likely to be true, which is that stringnet models can realize every phase that can be described by a commuting projector Hamiltonian. So if this sort of says they're kind of the best you can do if you want to build models out of commuting projector Hamiltonians, you're never going to get any phases, any additional phases beyond the ones the stringnet models can give you. It's a conjecture, but probably plausible. We certainly don't have any counterexamples, but okay, so that's sort of what stringnet models can realize. Then I was just going to, what should I do in terms of time? I'm 5 minutes over now, Juven.
Don't worry, actually, some people even take 3 hours, so don't worry.
Okay.
Well, we should add that maybe we should pause now for any like general questions that people want to have, and then we can consider it the official end, but then we can keep going. Does that sound good?
I have an open question slide. Should I just go straight there and then people can ask questions and then I'll stop? So let me go straight to open question slide. So this was going to be my last slide. So I just wanted to say a little bit about some open questions, at least in my mind, for what you can do with, we're related to stringnet models. So one direction you can go in is try to find stringnet models for symmetry enriched phases. So phases where you have symmetries. There's been previous work on the case where you have kind of the simplest case where you have finite unitary on-site symmetries. We kind of know how to build stringnet models with symmetry enriched stringnet models. But I don't think it's fully understood what to do for other cases, anti-unitary symmetries, continuous symmetries, non-on-site symmetries. So that's one possible direction for future work, which is trying to understand incorporating symmetries, more general symmetries into this construction. Another direction, which I think there's still some room for work, is on fermionic stringnet models. So there should be an analog of these stringnet models for systems built out of fermions. And there has been work on this by Xiaogan and Zhen Cheng and Zheng'an Wang. I think it's not complete though. So there's also some room for maybe trying to understand the general way to construct fermionic stringnet models. And this would give you hopefully the most general most general commuting projector models for fermions, fermionic topological phases. So, so anyway, I think I'll stop there for at least for any questions.
Yeah, I have a question about this commuting projector model.
I'm sorry, I can't hear. Can you speak more loudly?
I have a question about the commuting projector model you just mentioned. I wonder whether it's true that the commuting projector model always have a gapped boundary. Is that clear?
Yeah, that's a question I've wondered about too. I feel like okay, so when to be clear, we're talking about commuting projector models with finite dimension, things like, you know, for simplicity, right? Finite dimensional Hilbert space. I think it's plausible that that's true. I guess that's why I made that conjecture. But yeah, proving that is not easy, because you can always truncate your commuting projector model and get a spectrum with a gap, but the zero energy subspace will generally be highly degenerate, right? So to have a truly gap boundary, you should have a unique ground state. So you have to somehow split that degeneracy, and that's not obvious.
Thank you.
Michael, can I just ask a very simple clarifying question about this open question on fermionic stringnet models? So by that, I assume you certainly don't mean the type of stringnet models that you already described that happen to have fermions as a part of, as a type of anyon, right? But could you elaborate a little bit what exactly you mean by fermionic stringnet models? How is it different from the?
So these were, all the models I was talked about here were built out of spin. So it's a bosonic, the underlying degrees of freedom were bosons. And so the only topological phases we could build are what are called bosonic topological phases. Now there are also topological phases that are called, that you can build out of fermionic systems, like the Laughlin state or something. Maybe the Laughlin state isn't a great example, but there are some phases you can get from fermions that really have no, I don't know how much detail I should go into, but phases that are intrinsically fermionic, there's nothing like that you can build out of bosons. And so, yeah, you could try to build models for those, you know. The short answer is we want to build phases, we want to build models for fermionic topological phases. And those are topological phases where you have an underlying local fermion.
I see. Thanks.
Hi, Michael, can I ask a question?
Sure.
So it's related to your earlier comment. I think it was a response to Nati's question, but I'm not sure. But you made a comment that the Torah Code Hamiltonian, even I presume on the honeycomb lattice, would not be exactly the same to your stringnet model, you know, even ignoring just trivial constant shifts or multiplicative factors. So is my understanding that means that the stringnet model, I should not think of that as a fixed point model? Does it have some kind of short distance interactions between?
It's just the only difference is, okay, if you want to know the precise relationship, it's that basically the usual Torah, okay, so let's call the Torah Code Hamiltonian minus QV minus Bp. Then the stringnet version would have the same QV term, but it would have a different Bp term. We can call it Bp tilde. And what's the relationship between Bp tilde and Vp? It's pretty simple. It's basically Bp tilde is something like you take Bp, but you multiply it by a product of QVs on each side. So what does that do? It doesn't change the ground state at all, because the ground state, QV is 1. It just makes it so that it basically makes the matrix element Bp 0 unless the branching rules are obeyed on all 6 vertices. These are supposed to be the 6 vertices around the plaquette. So the product here runs over these 6 vertices. And so it's a kind of relatively trivial modification, leaves the same ground state wave function, but slightly changes the energy spectrum of the excited states.
Right, I see. That's interesting. Just to see if I physically interpret it correctly, this means that if you have an E anyon sitting somewhere, you can put an M anyon for free on that plaquette, which means there's like a short distance attractive interaction or something.
If you have an E anyon sitting there, an M anyon there, yeah, it costs 0 energy. That's right.
I see. Okay.
Wait, no, it costs 0 additional energy.
Yeah, 0 additional, exactly. The extra M anyon is not penalized.
Yeah.
Okay, interesting. Thank you.
Can I ask maybe a basic question on these constructions?
Sure.
So is there any sort of intuition on what happens if I make these branching rules more or less stringent? Like, is there some sort of universal behavior that I should expect if I allow, literally every possible trivalent graph in the model? Like, I guess, what does it buy me if I add more restrictions on these branching rules?
Okay, good question. So this is something I kind of skirted over. So the branching rules cannot be chosen arbitrarily. There's one extra constraint on the branching rules, which I didn't mention, which is called associativity. So what that means is that, well, roughly speaking, whenever you have a graph like this, like ABC, for any given A and B, there's some set of allowed C's. So we can write this as kind of a multiplication law, like A times B is equal to, C1 plus C2 plus, and the C's I'm writing here are the allowed strings that can live up here. And so now associativity is the condition that, like, if you take A times B times C, there are 2 ways to kind of calculate it, and you should get the same answer. So you can write this out as some condition on this delta symbol that I wrote down. There's some associativity condition on this delta symbol that says, it basically guarantees that if you fuse things together in these 2 different ways, you get the same possible outcomes. That you get the same possibilities up here with the same multiplicities. Anyway, you have to impose that extra condition for the instruction to work. And so you can't just choose the branching rules arbitrarily. So you have to choose them to be associative, and so that's a restriction, a significant restriction on the allowed branching rules.
Okay, thanks. That helps.
Mm-hmm.
Sorry, I have a quick question about the excitations. Maybe you'll address them when you go further on, but I just thought I'll sort of ask you now. In your original paper, you actually have a sort of a form of sort of a string operator for closed loops and sort of how to define excitations. But what is not clear to me is how you would actually end the string if you want to sort of categorize your excitations in terms of violations of plaquettes and vertices, or like what combination of plaquette or vertex violations correspond to a particular type of excitation. Is this something that sort of is worked out, or is like, what's a way to sort of think about it if one wants to derive this sort of relations?
Okay, so I don't know if I'll get to that or not, but the short answer is that at least the way we understand it, we construct string operators that build these anyons. How you terminate the string operators at the endpoints is there's some ambiguity. You have choices for how to do it, and somehow we don't care because different terminations give you the same anyon type. So basically, it's not the way we approach the problems. We just try to calculate the different string operators, and then we say different ways of terminating it. Just change some local properties of the anyon. I think what you're asking is whether there's some more microscopic thing where we can really, I don't know, really find some complete set of commuting projectors that we can use to characterize our anyons, just like we can in the Torah code, where we can say the E anyon, we can characterize it in terms of some projector it violates, and the M anyon. We don't use that approach. It may be possible to do that, but it's harder to do that directly in these models, basically because of this point over here. Even in the Torah code case, like if you use a Hamiltonian like the one we have, the E and M particles aren't as easy to categorize because, as Ruben mentioned, like if you have an E particle there, that an extra M particle causes zero energy, so it's not quite as well behaved as the Torah code Hamiltonian from that perspective.
Okay, thanks.
So when you say that the topological phase is related to the Drinfeld center, what do you mean? Because looking from a mathematical perspective, Drinfeld center arises only when the space is cylinder but not disk. But as far as I know, that what you discuss here are all disks. Is that right?
Yeah. So what I mean by it, and you may know more, but I don't fully understand the Drinfeld center construction, but what I mean is the following statement. The input into our construction is a unitary fusion category. Okay, that's what this F, roughly speaking, I think our input data is very close to that, if not equivalent to a unitary fusion category. Okay, the output data is a Hamiltonian, and any gapped Hamiltonian defines a unitary modular tensor category, with F symbols and R symbols, braiding and fusion, right? So our input is a fusion category, the output is this braided fusion category. And my understanding of the Drinfeld center is it does something similar. You can input a fusion category and it gives you a braided fusion category or a modular tensor category, whatever your favorite term is. And so my understanding was it's a similar thing, but it's a purely mathematical construction. It doesn't give you a Hamiltonian. And furthermore, my understanding was our mapping is the same as the Drinfeld mapping. So the output that comes from our fusion category has the same data as the output that comes from the Drinfeld center calculation. So that's what I meant by it. It's just input is fusion category, output is braided fusion category, and the braided fusion category you get is exactly what you would get if you use the Drinfeld center construction.
I see. Thank you.
Can I make a comment about that? I think maybe.
Please.
Yeah. So the cylinder that you're thinking of, Jinqing, is you can think of it as an annulus in the plane where the anyon is inside, right? Is in the middle of the inner circle of the annulus, and this algebra comes from. There's an algebra of these annuluses where you glue them together along their boundaries, which is given by drawing these stringnet diagrams and simplifying them as you combine these annuli. And the anyons are the central simple idempotents of this algebra, and that's the Drinfeld center. That's this Okeanu tube algebra construction, maybe you know. So that's where the stringnet pictures join the Drinfeld center.
Thank you.
Oh, maybe I can ask a small question. I've heard people talk about Torah-Vero invariance. Can you say a little bit about that in connection?
Yeah. So Torah-Vero invariance, if I remember correctly, they're kind of the space-time analog. Well, roughly speaking, the space-time analog for this stringnet model. So you input something like an F, some F symbol that obeys some Pentagon-like identity, and the output is it's a quantity you can compute for any closed, say, 3-manifold, and the way you compute it is you triangulate the space with tetrahedra or something. You fill it with tetrahedra, and for each tetrahedra you get like an F symbol, and you multiply them all. You do a big sum. It's called a state sum. But effectively, what that is doing is that's calculating, like, you can think of those Torah-Vero invariance as something like the partition function, the space-time partition function for this stringnet model. So roughly speaking, the Torah-Vero invariant is the space-time version that Lagrangian or version of this Hamiltonian. I think it's maybe not quite right. Like the closer one is something called the Barrett-Westbury one, but the Torah was the antecedent into that. It's like a special case, and you can think of it as a space-time version of this Stringnet sort of Hamiltonian description. And so it's an invariant that you can associate for every 3 manifold, but you can think of it as the partition function, space-time partition function of a certain Stringnet model. Does that answer your question?
Yeah, but thanks. That was helpful.
Michael, question. So one thing is that how about the generalized Stringnet model that you also prepared? Can you comment about that or go through them?
Oh, the generalized Stringnet models?
Stringnet model. Sorry, my internet somehow is unstable.
Yeah. So what I told you was the generalized Stringnet model. I had a slide which was comparing them with the original construction. I could tell you about that, but that I don't know if I should do that yet, or well, it's up to you guys. You guys are the hosts or whatever. Should I tell you? I had 1 or 2 things to say about the relationship between the generalized Stringnet construction and the original Stringnet construction. I don't know if that's what you're asking, or if you're asking something else.
Yes. But okay, maybe people can ask more questions, and until no more question, at least at this moment, and you can go through those slides. I do have another question though. So you mentioned this commuting projective Hamiltonian. You hear me?
Yes, I hear you.
Projective. I wonder whether the Hamiltonian you write down basically just as 2 operators, usually called A term, B term, or maybe you call Q term and B term. I was wondering whether the necessary that all these class of Hamiltonian should be represented by this 2 type of Hamiltonian. Basically, it's just like 2 operators. Are there? I mean, in general, are there some phases that you cannot obtain just by 2 types of operators?
You mean commuting projector? I think this is related to this conjecture too. You're saying, could there be commuting projector Hamiltonians that can realize phases that are outside of this class of phases? In particular, could there be commuting projector Hamiltonians that require 3 different types of projectors or something? Is that what you're saying?
Yes. Almost.
Yeah, we don't know, but I guess the conjecture is saying no, that because the conjecture says the Stringnet models realize everything, and the Stringnet models only require 2 types of projectors. But okay, I don't, as I said, I don't really have a tremendous amount of evidence for that conjecture. It's other than the lack of counterexamples. So maybe such things do exist. It would be very interesting if one could find an example.
Okay. So as far as you know, there are no examples from the current literature to maybe construct solvable model with 3 or more types of operators, maybe A term, B term, C term, etc.
Oh, there are probably examples with 3 types of projectors, but I'm saying I don't know of any examples where they can realize a phase that cannot be realized by the Stringnet construction.
Thank you.
So may I clarify a point? So we start with a unitary fusion category whose simple objects would be the set of labels, right? And then you construct a Hamiltonian. But suddenly you get an output, which is the Drinfeld center. Like what happens from the Hamiltonian and the output? Like what's your consideration between these?
Okay, so I think maybe what you're asking is, how do we go from a Hamiltonian to the anyon types, like the anyon the unitary braided fusion category? How do we get from a Hamiltonian to unitary? So physically, this may not help you, but just for the other audience, like physically, any Hamiltonian, it's believed any gapped Hamiltonian will always have particle-like excitations, and you can always define by actually pretty operationally define an R symbol that describes those excitations and an F symbol and so on, and will define some unitary braided fusion categories. So that's the general picture, is that for any gapped Hamiltonian, we should have a unitary braided fusion category. Now, what you're asking perhaps is more concretely, do we have like an algorithm to compute from our Hamiltonian the corresponding unitary braided fusion category? And
no. What I mean is, like, so you say if we have a gapped Hamiltonian, then we should have, right? What is should have? Like, what does should have mean here?
So physicists believe that if you have any gapped Hamiltonian, you can you can look at the excitations of that Hamiltonian above the ground state, and you can classify the excitations into different what are called super selection sectors, where you say two excitations belong to the same sector if you can get from one to the other by a local operator. And then they believe that you always get a finite number of super selection sectors. And then once you have those finite number of super selection sectors, you can then construct operators that move those excitations around. And then once you have operators that move them around, you can define there's a way to actually very operationally define an F symbol and an R symbol. And so there's kind of they believe that if you follow all those steps, the output will be an F symbol, an R symbol, fusion rules, and all this data. And furthermore, all that data will obey all the constraints of a unitary braided fusion category. So that's the belief, is that if you start with a gapped Hamiltonian, there's a procedure for finding excitations, then starting to analyze what happens when you move them around, and then extracting an R symbol and so on. And in microscopic, in various models like these, we can actually follow that. There is, pretty concretely, but it is a conjecture. We don't know for sure that gapped Hamiltonians will always give you, for example, a finite number of objects. That's believed to be true.
I see. Thank you.
May I ask a question? It seems that you put the model in 1+1D spacetime, right?
Well, the Hamiltonian is 2+1D.
2+1D.
Yeah, the Hamiltonian, because remember, it was a spin model on the honeycomb lattice, right? So if we go back, oops, sorry, there's a little bit of delay here for some reason. Where did I have it written down? Yeah, here we go, right? So here's a picture of the honeycomb lattice, right? So each one of these dots is a spin, and this is supposed to form a whole 2D lattice. So we have a 2D spin system, and of course there's the time direction on top of that, right? If you write down the full dynamics of your system. So it's 2+1D. It's a two-dimensional Hamiltonian that we're going to write down. However, maybe what's confusing you is that the kind of motivation for our original way that we draw our string net diagrams is thinking about them as 1+1D whirl lines. So,
I was wondering, how can we define parity symmetry and time reversal symmetry in such a model?
For this two-dimensional model?
Yeah. Can you write down explicitly or explain it in brief sentences?
Right. So for time reversal symmetry, of course, you have different options. Time reversal is usually, at least the way I think about it, is basically any anti-unitary on-site symmetry you could call time reversal. It's sort of up to you. So for example, one way you could define time reversal symmetry is it could just be complex conjugation in this basis, this string net basis. So what that means is that it's an anti-unitary symmetry. And so in this, you take if you want to know how it acts on some state, you write the state in this string net basis, say this 0, 1 basis. You'll get some complex numbers when you complex amplitudes, and you just apply complex conjugation of those amplitudes. So that's one way to define time reversal. Now, it's not at all clear that the Hamiltonian will be invariant under time reversal. Sometimes it will, sometimes it won't, but that's one way you could define the time reversal operation if you wanted to. in such a system. So it's complex conjugation, let's say, in this basis. But that's just, you could say, an arbitrary definition. Maybe the only virtue of that definition is that for some significant fraction of models, it would be time reversal invariant. But it's still a bit arbitrary.
Yeah, why I ask such a question is that if a system has a time has PD symmetry, then the Hamiltonian is not necessary to be Hermitian. So maybe we can use such a symmetry to release the Hermitian condition.
Right. That's interesting. Yeah, I haven't thought about that, but that's right. Yeah, and I guess for parity symmetry, it's maybe even easier. You could just define it by rotation, 180 degree. Oh no, let's see. You want parity, you want reflection. Yeah, we could do reflection about, I don't know, the vertical axis or something. Yeah, it would be interesting.
Yeah, thank you.
So I don't know, are there any other questions, or what should we do next?
Yeah, so it's up to you. If there are no more questions, well, people can leave, of course. You're free to go at any time, but yeah, if I know we cut you off in the middle of discussing all of these conjectures, if you'd like to go back to that, you can. If you want to just finish.
Well, what I have, I mean, sort of up to you to some extent. What I have are there are a couple more things. What I plan to talk about, I didn't plan to talk about the anyon excitations because I didn't think I have enough time, but I do have some slides on that. The other thing I was going to talk about was just quickly the relationship between the generalized stringnet construction and the original stringnet construction. So those are the two options. I could talk about either one or both of them. The relationship is shorter.
But relations is interesting to me.
Okay, so that's easier and that's shorter. So I can quickly talk about the relationship. This is maybe more for people who are really getting into the details, but so what is the relationship with the original construction? So I said that these generalized stringnet models were a bit more general. The original construction made some unnecessary assumptions. So here I just want to say a few more words about that. So basically, what was the original, there were two extra assumptions, the way I think about it, in the original construction, both of which restricted the generality. So one assumption that was made in the original construction was that you could define, the wave functions were defined, and it was required that they were invariant under arbitrary planar deformations of the stringnet, not just deformations obeying, there was no vertical axis. First of all, there's no time-like axis, and we required the wave function to be invariant under arbitrary deformation. So for example, like this is a picture one, right? So the amplitude you could take a diagram like this and just like twist it, like rotate it however you want, because there's no rule about no vertical bending or anything like that. And the claim, the requirement was that you could define an amplitude phi, which obeyed like all the local rules that we wrote down, but also obeyed this stronger constraint. So you could just distort your diagram however you like what I drew here, and the amplitude is the same. Okay, so this is a extra condition, and so it's full topological invariance. I think in our paper we said it's just topologically invariant. So we imagine these planar graphs, you would draw them. We put orientations on them because we didn't have this time axis, and we said it should be invariant under arbitrary deformations of these graphs. Okay, so that we're not assuming that here. So that was one extra assumption that was made there.
Michael,
the other assumption,
question about this assumption. So in fact, intuitively, it sounds reasonable for the following reason, right? So if I understand correctly, all the known stringnet models, they flow in the low energy to some garden variety, 2+1D TQFTs. And TQFTs has Lorentz symmetry. So it's kind of intuitive that we would like to demand this rotation symmetry in assumption one. But technically, I know that cannot possibly be right because you will miss some model as you are going to discussed. So I'm just wondering, do you have any intuition, like from a low energy Lorentz invariant point of view, why there's a preferred time direction in this construction?
Oh, yeah, I don't have anything deep to say about that. I think it's just, you know, I think the point is, yeah, the statement that it's Lorentz symmetric is some, Lorentz invariant is some statement about, yeah, the underlying emergent structure, you know, the anyons and their statistics certainly don't care about their rotational invariant. It's topological, in fact, right? But that's no guarantee that you can build it from a microscopic model which has that symmetry. So, I mean, now, I don't think that, I don't know, yeah, it may very well be that there are other constructions which have the full symmetry at a microscopic level. But maybe all I can say is if you try to use this particular approach for building the systems, if you impose this microscopic symmetry, it seems to reduce the generality. But I don't know if that's a fundamental constraint. There may be other constructions which preserve the symmetry. And in fact, I should say that, you know, there are choices of gauge you can make. I mean, it's also kind of gauge dependent, even within the stringnet construction. For some choices of gauge, you can make this work in our, for some generalized stringnet models, there exists a choice of gauge where this holds. And so it depends on the choice of gauge. It's a very detailed question. But if you require this, there are some models where for no choice of gauge can we ever make this work. And so that's why it seems to restrict the generality.
Can you give one example that one cannot realize using the original stringnet model? Maybe is it true that the quantum double of the twisted Z3 cannot be realized?
Z3, yeah, that's what I was going to say. Yeah. Okay. So the simplest example that cannot be realized, not that it's the twisted quantum double. So Z3 Dycroft-Witten theory with some non-trivial co-cycle, it cannot be realized by this rotational invariant. It has to do with something called the Z3 Frobenius indicator, basically. I could say more, but when you have three string types that are all the same that come in, you can have a situation where if these are all A's and they're all coming in, there's kind of, there can be a situation where rotating that vertex by 120 degrees should give you a third root of unity or something. And so if you require that the rotation doesn't give you a third root of unity, it kind of throws out some of these phases.
Right. Okay. Thank you.
Okay. So, yeah. So that's one restriction that we were assumed that they had arbitrary planar deformations. It was invariant under arbitrary planar deformations. The other constraint that was imposed was we assumed that if you look at kind of a picture like this picture, you can think of this as kind of like a tetrahedron. If you imagine, you know, you're kind of on a sphere or something, you're just looking at, well, we viewed it as a tetrahedron. We thought of it as a tetrahedron, and we assumed that that this amplitude was invariant under all symmetries of the tetrahedron. So now there's different types of symmetries. You could rotate the tetrahedron. That's already covered by this guy. But you can also, since we were thinking of it as a tetrahedron, there's also other symmetries. Like, for example, you can reflect it. We assumed it was invariant under reflection symmetry. And we also assumed it was invariant under, like, all the symmetries of a tetrahedron. I can't remember how many, probably 24 symmetry transformations. We assumed that was invariant under all of those. And this was motivated by the idea that our wave function could be defined on a sphere. And so these tetrahedral symmetries are either reflections or rotations on the sphere. And we thought that reflections wouldn't restrict the generality because we thought we couldn't build. We thought time reversal symmetry or parity symmetry was fundamental to these models. And then the other things we thought, oh, well, it's on a sphere anyway. So these are kind of spherical rotations, if you like. So we imposed both of these conditions, kind of planar deformations and also these kind of spherical rotations and reflections, which was encapsulated in this one requirement that the amplitude of a tetrahedron is invariant under all tetrahedral symmetries. And both of those conditions restrict the generality. And so as a result, yeah, it's not fully general. There's some phases that can't be realized. And yeah, one example is the Z3. The Z3 one is already, even the first assumption violates it, this one. And there are also models which you can realize this way, but which are impossible to realize when you impose this tetrahedral symmetry. So both of these are restricting the generality, and so we're relaxing both of those in the generalized models. We relax these two conditions.
Can I ask a question? So about this no bending condition, does that mean that there's going to be some kind of, like, say I wanted to define this model on a sphere, then I can't choose this special direction consistently, right? There will have to be two cowlicks. So is there actually like a non-trivial framing dependence in these models? Are those like defects?
So I think, I don't know if this quite answers your question, but there are obstructions. Let's see, if you define it on a sphere, there can be issues. Let me try to remember what the issue is. See if I can remember. I think you can end up in a situation where I don't know exactly what the status is on a sphere, but I think you can end up in a situation where one of your projectors has to be violated. Like you can't make all of the projectors equal to 1 on the sphere, at least in some models.
So that's very interesting, because that's kind of like this when Z type terms, right?
You mean?
It's like curvature response to C, because the number of violations, or not violations, but like if you think of this preferred direction as a vector field, the zeros will give you the Euler characteristic. So
right,
isn't that a bit like what the when Z term does?
I mean, you're saying it has something to do with curvature, I guess is what you're saying. And that's true. Yeah, I don't know. Yeah, I don't know what significance it has, but yeah, you're right. It does seem to be true. It's not a problem on the torus. I think that's right. It's a problem on the sphere. Yeah, I don't know what significance that has. It's yeah, possibly there's some significance to this not working on a sphere, but I don't think it means that the phase, that there isn't some model you can write down on a sphere. It's just that it won't have all the properties you want on the sphere. Like you can't make the wave function spherically isotropic. Like it has some, as you said, some special points, and yeah.
And you say Z3 digraph-Witten theory already does something like this?
Z3 digraph-Witten theory is already impossible to define on a plane with, yeah, make it isotropic. That's right.
I see. Thank you.
Okay, so I think that was all I was going to say about.
Is that the property of Z3 digraph-Witten has something to do with maybe the eigenvalue, the T matrix eigenvalue is not paired by complex conjugation relation. For example, like double Fermion, the T matrix, there's I and minus Z3.
That's not the fundamental issue, because let me give you another example. Z4 digraph-Witten theory can be realized in an isotropic way. So there's no obstruction for Z4 digraph-Witten theory, or at least I'm trying to remember. Yeah, that's right. Yeah, I think Z4 digraph-Witten theory, we can do it. And that one also is not time reversal invariant. So it has the same property you're talking about, that there exists anyons that don't have pairs. But the difference is that the Z4 one doesn't have the being a sure indicator issue, because Z4, so you can't have 3 string types that are all the same coming in. So yeah, I mean, I should just mention one other thing since we're getting into these details. There's probably another way to deal with this time axis, which is something I did in a paper, another paper, where you can, instead of introducing a time axis, you can let things be isotropic, but then you have to put a dot or something on the vertex, on each vertex. This dot deals with this issue. It keeps track of kind of, one of these, it breaks the symmetry between the 3 vertices. So now your diagrams, you can draw arbitrary diagrams, but you have to put a dot anytime you see a vertex with 3 identical strings that come in. That dot tells you kind of which order you should read the 3 edges. So we, in a paper, we worked out a way to do it this way. So without introducing a time axis, you could define these diagrams. But we only did in the abelian case. I suspect you can do it in the non-abelian case too, but this is an alternate way to deal with this issue, is to decorate your vertices with some extra dot or something that tells you which, allows you to break the symmetry between the three edges. And then that way you don't need to have a time axis. And as I said, we did this for the abelian case, but we didn't work it out in general how it works in the non-abelian case. We found the time axis formalism is just more convenient. It's more natural somehow. It's just easier, I guess, to work with. Okay, so that was all I was going to say that in terms of what I planned to say. I had a couple things on anyon excitations. I could show them if you want, or we could stop.
Well, I'm happy to have a look at the what you plan to show us.
Okay, it's not much. It's pretty not very detailed, but just give you a flavor maybe. So how do you construct anyon excitations in these models? So the way we think about it is the anyons are created by applying string operators to your ground state. And so you apply a string operator like on this red curve, and it creates two anyons at the two ends, here and here. And so the idea is that for each anyon type, there should be some corresponding string operator, W alpha. So for each anyon type alpha, there's some corresponding string operator, W alpha, that creates it. And W alpha is a function of a path P. So you draw some path on your lattice, and then you get some operator, W alpha P, and then that operator will create two anyons at the two ends. Anyon and its antiparticle, the two ends. Okay, so now the question is, how do we construct, before I get to how do we construct it, this W alpha P is not just some arbitrary string-like operator. It has to obey a certain property for it to be kind of a good string operator. It has to be path independent. So what that means is when you apply to the ground state for two different paths, let's say joining this, if you take two different paths that join the same endpoints, it should give you the same state. So it doesn't matter how I draw the path. It only depends on the two endpoints. The action on the ground state only depends on the endpoints, and that's important because if that weren't true, then this string operator would presumably be creating excitations somewhere along the path. But this path independence guarantees, because you can move the path wherever you want, that it could only be creating excitations at the two endpoints. It can't be creating them anywhere else because you can move the path, right? So now our task to find anyons, the approach that we take to find anyons is to just look for path independent string operators. And the idea is for every anyon, there should be a path independent string operator. So if we can find sort of the basic path independent string operators, we can find the anyons. So then how do we find path independent string operators? So we just have an ansatz. It's kind of a guess for what the string operators look like. And then given this ansatz, we can we can use it to construct them. We believe our ansatz includes everything, but we can't, it's a conjecture. So how does our ansatz work? So our ansatz is that the string operators have the following graphical description. So when you apply the way to think about when you apply some string to some bra, which I've written here, it adds a type alpha string, and which I've drawn in red here, underneath the string net. So I've drawn it underneath, like it's below, like it's under crossings at each of these. Not that that's so important, but that's our convention. So we draw it underneath the string net diagram. And then once we draw that, the next step to figuring out the action is we have to somehow simplify this diagram. So we have some rules for how to do that. So one rule says, anytime an alpha crosses under some string A, you replace it with a picture like this. So here's the alpha string has been replaced by an R string and then an S string, and the A string is still here, A and A, and then where they cross, you have some other string B. So you replace it by something like this, and then there's some coefficients here, which I'll talk about in a second. And so that's what you do. At every crossing, you make this replacement. And similarly, at every crossing this is a crossing where alpha's on the left. This is a crossing where alpha's on the right. When it's on the left, you make another replacement with some omega bar. And here, omega and omega bar are some complex parameters. They're basically matrices. I could tell you in more detail what they are, but roughly speaking, it's some collection of complex numbers. And once you specify these omegas, it's going to define our string operator, okay? And so how does it work? So the first step is the one I've already said. You draw the string underneath. The second step is you replace all the crossings like this. So let me show how it works. So you draw it, then you replace all the crossings here. You would replace with the diagram. I don't know if you can see it, but if you, this picture here is supposed to look like, whoops. I don't know, this is not working for me, forget it. Yeah, so I've just, I've replaced the red string with these diagrams. And then the final thing, and there'll be some constants here, which are just like these omegas. And then the final thing you do is you need to reduce it back to something on the same lattice, to get an action of your string operator. And so you play the same game as with the BP operator. You reduce this diagram to this diagram, again, using the local rules, right? And so you can use those local rules to reduce it. And the net effect is that the states on these links, which were A, B, C, D originally, are now going to be some new things because you've fused this string on. So it's going to be A prime, B prime, C prime, and D prime. And you're in general going to get some sum over those. And then there'll be some constants here, and that tells you the action of your string operator. So it tells you when you act a string operator on the state A, B, C, D, you get this linear combination of states. So these constants are going to be determined by the omegas. That appears in this first step. And then by F's and Y's, that appears in the second step when you reduce from here to here. And so there'll be some expression here that's going to depend on omegas, F's, and Y's, and that will tell you how your string operator acts. And so our ansatz is that this that this is how you can construct your string operators. Now, one thing I should say is in general, this string operator will not be path independent. Like if I just pick some random omegas, there's no reason it will be path independent. So you have to search for special omegas which make it path independent. So it turns out the question of path independence can be reduced using it's not hard to show, to certain algebraic conditions. And so I've written them here. There are 3 conditions on these omegas. The first one looks kind of like the hexagon equation. People are familiar with that, though it's not quite the hexagon equation. And then there's some other conditions. So there are 3 conditions. And if omega obeys these 3 conditions, you get a nice path-independent string operator. And so then the basic procedure that we follow is we say, we want to search for solutions to these equations star. And we conjecture that these string operators of this type create every anyon excitation. So if that's true, then that means that by solving these equations star, basically finding a complete set of solutions, or more precisely, a complete set of what are called irreducible solutions, you can find all the anyons. So you can find not just the anyons, but maybe even more interestingly, we get the explicit string operators that move the anyons. And so that's the way we approach the anyon problem. Is we write down an ansatz for string operators, and then we conjecture that this ansatz is complete. So if that's true, basically the question of finding string operators operationally, finding anyons, comes down to solving these equations. So you're given F, but you have to solve for the omegas. And in general, we can do this in some examples. You'll find a finite number, at least in the examples we work out, finite number of irreducible solutions. And then there's one for each anyon type. And once you know that string operators, of course, you can calculate all the statistics of the anyons, anything you want, because you know how to move the anyons around. And so
is that a quick can you relate these to the tube algebra? You know what I'm talking about?
You're asking me?
Yeah.
I don't understand the tube algebra very well, so I don't know.
Because that's a very similar looking thing where you're solving for the anyons, but you're solving for these projectors. Whereas here you have things that sort of square to, well, no, you have this equation. They're not projectors, right? These omegas?
Not projectors. No, it's not projectors. Now, I don't, the tube algebra story I've seen at some level, but I don't know in detail enough to really give you a good answer. I think that I think it's a different approach. I'm not sure if it's a better approach. It's just a different approach. It may even be a worse approach, but it's a different approach where we try to explicitly construct the string operators that move the anyons.
Yeah, I just think it's nice because the tube algebra kind of gives you like, it shows you what the end of the string operator looks like in some sense. Like it takes strings that you already have in the model and it defines like little bubbles for them at the ends.
Yeah. Yeah. You know,
operators too.
Yeah, I don't know the. Yeah,
I
don't have a good answer to your question.
Okay, thank you.
Michael, in this construction, alpha is the anyon type, correct? So when you write down W of alpha, subscript alpha?
Yeah.
Right. So how is it a trial and error process? How does one know ahead of time? For instance, whether you're going to end up with like a Fermion model where there is only one type of anyons, whether it's a Torah code where, you know, alpha could be E and M, and therefore there are two different kinds of strings. Is there any intuition you get, or you just have to try and solve the equation star, assuming alpha runs?
Yeah. The only thing you know, okay, there probably are more things you can say than this, but I only know one like very simple constraint. It doesn't tell you the number of anyon types, but it does. You can tell the total quantum dimension. So each of these anyon types has a quantum dimension defined, of course, and we call that d alpha. And so you can define something like sum of d alpha squared over all alpha, and then this thing is going to be equal to the sum of ds squared over all s. Squared. Okay, so
what is ds?
So that I think ds is defined to be, it's in terms of y. I define it in terms of y. It was like something like this. It was the value of this loop, this bubble. So for every string type s, there's a quantum dimension of the string type that we talked about. Okay, so this is a quantum dimension that's associated with our input data. It's a quantum dimension that appears in unitary fusion categories. And the d alphas are the quantum dimensions of the anyons. It's a quantum dimension in the output, the unitary braided fusion category. And so there's a relationship between those two, which is this. Okay, and so that's known to be the case, at least under the Drinfeld center construction. It's probably true for Stringnet models too. And so, yeah, so that gives you some constraints. So you kind of know what the total quantum, that gives you an upper bound on how many particles there can be, because every anyon has a quantum dimension of at least one. So if you calculate this, let's say for the, you know, and you get some number like 15.39, you know there are at most 15 anyons in your model. So then you can try to find 15 irreducible solutions to equation star. Right? You try searching it. If you actually don't know, I guess you kind of know when you're finished, because as you start calculating them, you can calculate the d alphas and see, have I saturated this thing or not? You could keep, I don't know if it's the most efficient way to proceed. I definitely don't know that, but in principle, you could do something like, we've done it in a couple examples and we can carry it through.
But it's not obvious by staring at these equations, right? Or
what's not obvious?
That the relation between the total quantum dimension.
No, I didn't even define,
you didn't even define, right?
It's not obvious. No, it's not obvious from these equations. Yeah, I think it's a not an obvious result. Yeah.
Okay.
But, you know, I can say this, you know, we kind of conjectured this result even before we knew much of the math, because you can easily see it's true for all gauge theories. It's like, these are like identities you're familiar with about sums of squares of representations and things like that. So you can see it's true for gauge theories. You can see it's true for the double topological phases. So then you're like, oh, it's got to be true. But yeah, it's not obvious from what we've written. So that's all I had to say, I think. Yeah, that exhausts all my slides.